Let's see. Yeah, so I'm going to talk about the XZ Utils Backdoor, which, like Jay mentioned, it happened a couple months ago, or actually, sorry, just 1 month ago. There was a bunch of news headlines talking about a backdoor in Linux, basically. You know, did one guy just stop a huge cyber attack? Here's how millions of Linux computers almost got hacked, and it was in kind of both mainstream news and also like technical, or it was in technical news and also some of the like actually made its way to mainstream news. And when I was going through and reading all of these, they all kind of, they give some context and they talk about, you know, what cyber attacks generally look like and what the implications of this one are, but they usually don't go into too much detail about the specific components of like what actually goes into something like a backdoor being inserted into like a public open source repository like, or open source code like the code that goes into Linux. And so that's kind of my plan for this lecture today, is just to go through the specific details of how this backdoor works, the different components of it, and how it was put in place. And a lot of that ties in really closely with what we've been doing kind of in the past couple weeks with dynamic linking and ELF loading and disassembly and stuff like that. It all connects really well to some of our course material. So my general plan is just give first a little bit of background on open source development, because like I said, the backdoor, it was in open source software, which is a little bit unusual. And so this all really revolves around open source development. And so I'll give a little background on what that actually looks like. And then I'll also talk about kind of a timeline of how the backdoor is planted. So because it was open source, we can actually see this full timeline of how it was inserted and how the attackers actually got their malicious code in place. And then the next two sections are just kind of the technical details, how it actually works, and how we figure out how it works, which is via reverse engineering. And then at the very end, I'll talk a little bit about like attribution, who we think might have actually done this attack, and also implications, the greater implications for open source and for cybersecurity as a whole. So just kind of jump right into the open source stuff. Open source, as you guys probably know, it just means that software that's developed and published with its source code. So when you publish, closed source apps are something distributed by a company. They'll probably distribute just the binary. They won't distribute the actual the actual code with it, as opposed to open source, where you actually have the code distributed with the application itself. And because the code is usually public, the development process is also usually public, so it happens kind of in the public eye, and that's what separates from closed source code. And this is kind of my general overview of what open source development looks like. There's some main repository, something stored, usually hosted on GitHub or something, that is the kind of official definitive version of the software. And then contributors, which can be anybody. Anonymous contributors can fork their own copies of this repo, make changes to it, and then request those changes to be actually pulled into the main version. And then a maintainer is kind of a person who is responsible for the main repository, and they actually accept or reject code, submitted by anonymous contributors. And every once in a while, a maintainer will decide that the code is in a stable state, and they'll take a copy of the code on a certain commit, and they'll make it a release and distribute that as like this is the 1.0 version of this particular piece of code. The idea is that all this happens in the public eye, which in theory, the argument is gives a lot more review, and it allows more people to actually see the code, more chances to find bugs, and in theory, more chances to find security vulnerabilities. But we'll see that this is kind of an example of how that might not necessarily be true. So kind of the prototypical open source project is Linux. This is what we use on Spock. You guys have probably used it and heard of it before. Linux, the term itself, is a little bit vague. It kind of specifically refers to the kernel, which is this core bit of software that does memory management, hardware interface, and stuff like that. But when you actually download Linux, you're downloading an image that is a distribution, which is that core kernel code, which is just one open source repository, packaged with a bunch of other also open source repositories. So Debian maintainers, for example, take a bunch of other open source software, package it in with the kernel, and put it all into a single image. And that software is things that actually make the kernel usable, like a shell and remote connection software and package managers and things like that. And that gives us this really kind of complicated structure. So this is a kind of a comic that's been passed around a lot since the XZ Utils thing. It gives us this complicated structure where a lot of the world's critical infrastructure runs on these Linux servers, which are images that contain a bunch of open source software from all these different packages that have all these various dependencies. And as they go down, you end up potentially with the scenario where there's some single tiny little project that everybody kind of depends on. Yeah, is there a question? Yeah, System D. Yeah, so systemd it's kind of like a little like suite of, it's not little, it's pretty big. It's a suite of a bunch of different things that all like run. It just does a bunch of random stuff that operating systems need, like running long-running services, like SSH. The SSH daemon, which we'll see later, is a long-running service that listens for SSH, and so systemd is the that's where that it's a suite that kind of manages that and a bunch of other utilities. So not every Linux distribution is going to include systemd. But yeah, you end up with a situation like this where everybody depends on this one little package, and a lot of these packages are maintained by just hobbyists, people who aren't paid, just people who are doing it just for fun or as kind of a side gig. And sometimes, if there's some kind of like a bug, or in this case a security vulnerability in one of those, it's going to propagate all the way up to all this critical infrastructure. And that's kind of what happened with XZ. So XZ is a package that's used in Linux. It's a compression library, and it's relatively minor. It's small, maintained by just one guy. But there was this backdoor inserted into XZ, and that caused, or almost caused, a huge number of downstream versions of Linux to be vulnerable to this bug. So now this next session, I'm going to talk about like kind of the timeline. This is interesting. This shows like how the attackers actually got the backdoor in place, and we can actually see, like I was saying before, we can see all this because the project is open source, which gives us kind of a level of insight into how the attack actually happened that you wouldn't usually see with some kind of a closed source attack. But it started all the way back in the late 2000s when XZ Utils was first created. It's just, like I said, it's just a compression library. These new compression formats were developed, and alongside them, people developed tools to actually compress and decompress from these formats. And this guy, Lassie Collin, one of the people who developed these file formats, he made some tools and decided to maintain these tools specifically for Linux. So he made Linux packages that actually do compression and decompression, and they're they're distributed as like shared objects, and they're inside some package that contains a shared object that allows you to actually call a C function that will encrypt or compress or decompress into this format. And it gains popularity. It's super useful for particularly for software distribution, I think. And so it gets integrated into a lot of major distributions. Distributions start packing XZ into their code kind of by default. Pretty much every major distribution includes XZ at this point. But like a lot of open source projects, after a couple of years, development starts to slow. And this is relatively common. It's just one guy. He's not getting paid. And fewer people are contributing, and he's not really that motivated to keep continuing. And that's kind of fine for a lot of these open source projects because there's not a ton of super novel innovation going on to maintain a package like XZ Utils. So it kind of sits in this stable state of just being like maintained to fix bugs and security patches and some minor new features now and then. That's until 2021. That's kind of the state of things in 2021. It's everywhere, but it's not super well maintained until in 2021, this new contributor, which, like I said, they're anonymous, starts sending new patches to the mailing list. This guy, Giatan. And as we'll see later, this Giatan, it's a fake account used by the attackers to actually insert the backdoor and actually like put this malicious code into the XZ Utils library. And at first, though, there's no way to know that. His patches seem perfectly legitimate. They're fixing real bugs. And after a couple months, which is not that uncommon of a timeline, those patches get merged into the actual main XZ Utils repository. But the fact that it did take a few months is something that the attackers jump on. And they kind of do this two-sided thing, where on one side they have this new guy show up who's willing to put in a bunch of work and fix patches. And then on the other side, they start lodging a bunch of complaints on mailing lists and things like that. They start creating a number of fake accounts, sending kind of mean messages to the developer, to the maintainer, saying, basically implying that the development is too slow, and saying that he should choose a new maintainer. And you see things like patches spend years on the mailing list, or progress will not happen until there's a new maintainer, or like over 1 month and no closer to being merged. It's a bunch of these fake accounts which have since been kind of discovered as fake accounts, applying a bunch of pressure. And at first, he kind of apologizes and pushes back a little bit, but he also gives the attackers a little bit of a nugget. So he says, he hasn't lost interest, but he has a life, and it's a hobbyist project, so he can't put too much effort in. But then he does mention, recently I've worked off-list a bit with Giatan, and perhaps he'll have a bigger role in the future. This is kind of foreshadowing to what will come, because it's evidence that this strategy is working. He's realizing that because of these complaints, he can't maintain this stuff on his own, and there's this new guy who's being super helpful and doing a bunch of work. They kind of ramp up pressure, these fake accounts. They keep saying, more aggressively, you choke your repo. Why wait so long to change maintainer? It's important to be aware of everyone. It's just kind of mean, nasty comments, which is kind of lame. But this last one is the first one that actually mentions Giatan specifically. It says, Gia, I see you have recent commits. Why can't you commit this yourself? So this is basically asking, why is this new guy not a maintainer? And you can kind of see how this is a scary attack. And it works. It actually works relatively quickly. Within like 6 months, G10 gets put on as a maintainer of the project. And you can see, this is Colin's message where he says, as I hinted earlier, G10 might have a bigger role. He's practically a co-maintainer already. So you can see there's probably some like off mailing list communication happening, some private communication happening between them. And some maintainership is in progress, and that's what we actually see in the permissions. We start to see G10 now, he has like the actual permission to commit directly and make releases, and he's talking on mailing lists authoritatively as if he's like an official maintainer of the project. You can see where this is kind of a scary tactic because there's a lot of projects like this. There's a lot of crucial projects with that are poorly maintained. So this like two-sided thing, all you need is a couple fake accounts, and you can apply some pressure and then get your own account in there as made maintainer. But I mean, they're not done yet. Maintainers are still kind of observed, and so they spend a year just kind of laying low and just making perfectly legitimate commits to this XZ Utils library, which is kind of funny to think about. Like a bunch of security researchers or hackers somewhere, like their job for a year was just to maintain a compression library. But yeah, they just made a year full of commits, just legitimate commits that, as far as we know, aren't malicious. They did add some commits that like set up for the attack, but none of them were explicitly legitimate. It wasn't until like literally this February, a couple months ago, where they actually make the first malicious commit. And this commit, it's meant to be super unnoticeable. It's a commit that just says it adds a few test files. So it adds some binary test files, which is super common in a project. You'll have some binary files that you use to test the project on. And binary files are just binary, as are ELF objects. And so the point of this malicious commit is, it doesn't do anything on its own. It just adds a binary test file. But heavily obfuscated and actually encrypted within that binary ELF file is this new, encrypted within that test file, there is this heavily obfuscated binary ELF object, which is just a shared object that's meant to be linked into the larger lib_lzma_so, which is the final SO that's produced by this library. That heavily obfuscated ELF file is kind of all of the malicious code itself. It's meant to be linked into the larger library. And it exports some functions that it can get called, but it's still inactive. It's tracked by the repository, which is the first step, but it doesn't actually affect the real library code yet. And so a couple days later, they do like I was talking about. They make a release. They say, or G10 specifically makes a new release. And the important point about releases is that for whatever reason, releases aren't usually just a pure copy of the source code. Usually they include some changes to build scripts, some new build scripts that are a little bit different than what actually sits in the repository. And so that's kind of the gap that the attackers use to insert a malicious build script that actually does this process of injecting. So when this project is cloned and when the release is downloaded, when the project is built, and if you build it with the build scripts included in the project, which is how projects are usually built, it'll actually run this malicious build script, which is not included in the GitHub repository, but is included in the release tarball, the compressed release source code. If you run that build script, it'll actually do this process of injection. It'll do this process of extracting the payload from the test binary and writing it to disk as just an ELF object file, adding that object file to the linker flags while lib_lzma_so, this final shared object, is getting compiled. And then it also does a little in-flight modification. So just before it compiles some source code from the original repository, it'll slip in a little call, which it does with some bash commands. It'll slip in a little call that actually modifies this particular function, crc resolve, to actually make a call into this shared object. This is all statically linked. So everything gets statically compiled together into this one lib_lzma_so that ultimately is malicious. And so this is kind of my diagram of the overall structure of how this works. Yeah, so that's G10. He's the malicious guy. And at first, he commits this test binary with the payload kind of buried inside it. It just sits in the repository for a while. Eventually, he makes a release. And into that release, he puts this injector build script. It doesn't show up in the Git repository, but it does show up in the release. And then let's say somebody building a Debian image down there on a build image downloads this release, runs the build scripts, which actually builds this lib_lzma_so. But then because they're running this malicious build script, they end up extracting the malicious payload and kind of linking it in. So now we can kind of consider lib_lzma_so as malicious. We've got a malicious version. And then if they host that somewhere, for example, like on a package repository somewhere, and people start to download it, or if they distribute this image that they're building of a larger system, anybody who downloads that image or uses that package will then get infected. It now has this vulnerable library on their machine. And that's pretty cleverly done. I mean, none of this stuff is obvious because people do sometimes look at Git histories. None of this stuff is obvious. So the test binary is like quietly hid, or the payload is quietly hidden in the test binary, and this injector build script is never tracked by Git at all. So it's this kind of super silent way of inserting some code because he's a maintainer, because he has the permissions to do all this. He can kind of, without anybody noticing, inject this malicious code. And so this is kind of defeats that idea before of, or at least in part, calls into question the idea of open source necessarily being more secure because more people can look at it, because there's all these ways that maintainers can actually, surreptitiously include things that you wouldn't expect to be included in their repository. And then that was pretty close to actually getting somewhere. Yeah.
To clarify, so for the modified build script, so they're using GitHub as like their host and also the deployment platform, and that was a manually uploaded asset to the.
Yeah, so if you see in here, they upload the release tarball, so it's actually packaged. So there's two. The bottom ones are ones that are like auto-generated by GitHub, packages the source code, but that's not what most people are using. I think most people are using the kind of packaged tarballs, and so in those tarballs is actually where they put the malicious build script. And it's disguised as like some auto tools, auto config type thing, so it's pretty hard to find. And I didn't mention on the slide, the build script is kind of nasty, and I don't really think it's that interesting. But it just basically, it does kind of what I said, it just extracts and links in this malicious code. And so that was poised to actually like infect millions of Linux computers. Anybody who downloaded these updated, because distribution maintainers, periodically they download new releases, build them into their images. So anybody who downloaded an updated image that had a release in it would have been compromised and would have had this malicious library on their computer. That didn't happen, and it was kind of purely by luck. It was a Postgres developer, not actually a security researcher, a Postgres developer for Microsoft, noticed some unusual performance behavior while he was running Debian testing, which is a version of Debian that includes a bunch more like newer versions of packages just for purposes of testing. And luckily, he had kind of the background to do the investigation, and he realized that this was backdoored and sent this email to the open source security mailing list, which is like a public mailing list. And he basically said, after observing some odd symptoms, I figured out the answer. The upstream XZ repository has been backdoored. And this is the email that kind of triggered all of those news headlines and everybody in the security community to kind of panic a little bit and start checking around to see, like, are their systems compromised? How many systems are compromised? How can we roll back? Because this was integrated into some like testing distributions. Luckily, it didn't actually get that far. And then that same day, Red Hat, which is one company that manages the distribution, they give it an official number in some national database, and people start to do cleanup. And as another part of the cleanup, people start to do like analysis on how the malicious object actually works. And so that's what I'm going to talk about next, is kind of the details of how it works. But before we do that, are there any questions on kind of the process by which it actually was injected? Go ahead.
So, I mean, I guess I'm not very clear. So, like, there's a step where they can just kind of upload arbitrary stuff that, like, is not tracked in Git at all.
Yes.
No one necessarily looked at it.
Mm-hmm.
I guess, why is it so important that they managed to sneak in something that was tracked by Git? And like, why couldn't they have just like stuck the payload in like the part that isn't tracked?
Yeah, that's a good question. I think the reason is because like it's not that you can. It's not like I mean, it kind of is a free for all. You can kind of put whatever you want in there, but people are much more likely to notice if there's a random extra binary file. They kind of hid the injector build script among all of these other auto-generated build scripts, which are things that would usually, like there's a kind of common difference between, like most of the time, what's different between the release tarball and the repository is just some different build scripts. And these build scripts actually, like that's actually an automatic difference. It's this automated tool called like auto-config, and auto-tools let you kind of automatically do some build script automation before you release. And so it would have raised a lot more suspicion if all of a sudden there's this new binary object in there. And the binary object is like bigger, it's just more, like it's much more noticeable as opposed to like a little change to a build script. Other questions? So I'll kind of come back to what this means, like the fact that this is possible. It does have a lot of implications for kind of open source and security in general. But one of the things that I did kind of gloss over was how the shared object actually works. And this is where it really relates back to our course material. So like the idea is what we've gotten in that previous diagram, what we got was we have a malicious shared object that is loaded on vulnerable computers. And so next what I'm going to try and go through in kind of increasing levels of detail is how does that fact, how does having a shared object on a vulnerable, on like a target server, how does that payload actually work? How does it get you what's called like remote code execution, which is where an attacker can remotely connect to the vulnerable server and send commands basically as root and run them, which is kind of the gold standard of attacking some kind of a server. And like I said, I'll go into increasing levels of detail, but the biggest idea is we do command and control via the SSH daemon. So this is one of those long-running processes I was mentioning earlier. It's a process that runs on any server, like Spock, if you guys were connecting to it, you're using SSH. It's just a protocol for actually connecting to a server remotely. And in order to facilitate that, the server has this long-running process, SSHD. It's the SSH daemon that just sits in the background, waits on a certain port, and if a connection shows up, it will check the connection certificate and give it a shell if it's valid, if the certificate is valid. Otherwise, it'll reject the connection. So that's running on kind of any Linux server. Yeah.
I've heard like SSH.
Yeah, so SSH is like a protocol. It's a protocol for actually doing kind of remote communication over the network. And in particular, SSHD, this is like a particular implementation of that. And so you might SSH into something by using some kind of a client. Like if you're on Windows, you might use like PuTTY or something. And there's some kind of client software you use that encodes your communication in a particular format so that then it can be received by another SSH server, and it can decode that and actually give you like a shell. So that's actually, it's the format through which all of your commands to Spock are going. They get kind of encoded in this SSH format. And then the SSH daemon is the process that actually like receives those on the or at least receives the initial connection on the server side.
So it's basically
Yeah, it's a protocol for it. So the big idea with this is that, and kind of the reason why the attackers probably chose this particular project is that SSHD, this daemon, actually dynamically links liblzma. So if you remember dynamic linking from a couple lectures ago, we're going to go into a lot of stuff about that. But dynamic linking means liblzma SO gets actually loaded into the address space of SSHD at load time. And that gives us a lot of privilege. That gives the malicious liblzma.so backdoor a lot of privilege, and it's going to kind of leverage that privilege in order to hijack the SSA function that does certificate decryption. And so you can see I have a little mini diagram of how normally SSHD would work. It would accept a connection, check if the certificate is valid, and launch the shell. And what we're going to try and do is somehow replace or insert an extra little code path in here that checks the SSH certificate itself. Is it in a particular format that only the attackers know? And if it is, then we look inside there, and encoded in there, there will be some commands, and we extract those commands and execute them as root. Because SSHD is just a process, it can extract commands as root. So this is kind of the goal. This is the idea is we want to get from where we are, which is being dynamically linked in, to actually hijacking this little code path. And the specific way that the malware does this is by hijacking a particular function call. So this diagram I'm going to use a lot. It's kind of the memory address space of SSHD when it's running at various points. And it has, like anything else, it has a text section, and in there are some functions. And there's one function that, it's not actually called check certificate, but it's a function that does certificate checking, that checks certificates for an incoming connection. And as part of that, it calls dynamically linked library libcrypto.so, and it calls this RSA public decrypt function. And RSA public decrypt it just decrypts the SSH certificate. And the idea is, if we can kind of hijack that function call and make it point to our version, which is already dynamically linked in, we can force that call to, instead of pointing to RSA public decrypt, it'll point to our kind of evil version that inserts this extra logic and then kind of silently returns back to normal operation. And so that's the idea of how the malware actually works, but it comes with some kind of implementation questions. And the first two that I came up with were, first, like, how do we actually get that malicious code executed? Because we're a shared library, we're linked into the virtual memory space of SSHD, but we don't, that doesn't necessarily guarantee us code execution. Normally, usually you have to wait as a shared object. You have to wait to be called by some function in the actual main library or in the main code itself for your execution to actually happen. And then the second question is, assuming we can get our code executed, the code that we've stored in the shared object, assuming we can get it executed, how do we actually do this function call hijacking? And I'll start with that second question. Yeah.
What does C2, the SSH daemon, mean?
Yeah, sorry, that's just an abbreviation for command and control, just because it wouldn't fit on the slide there.
Okay.
Yeah, go ahead.
Was it actually called evil or safe?
No, and this is the thing. A lot of this, I've renamed a lot of these things to make them make more sense. All the names for symbols in the malware were named to kind of blend in. They were made to blend in with the larger liblzma shared object, so they wouldn't raise suspicion. Yeah, go ahead.
Why is SSHD, like, what does it need a compression library for? Like, is the
That's a good question.
Coming in compressed?
It kind of doesn't, and this is one of the one of the security things people have realized after this attack. They're like, why are we actually doing this? And they actually realized it a little bit before. This kind of accelerated the attack a little bit, but yeah, it shouldn't be. It's just because there's this kind of structure of it's actually systemd's fault. It dynamically links in parts of systemd, which then in turn link in this liblzma function. So, but there's no reason for it to need to, and I think since then they've made changes to make sure that it doesn't. But yeah, so I said I'll start with the second challenge. Assuming we can get our code to execute during normal operation, how do we actually do this function hijacking? We can't just modify the text section because you guys remember text sections have read-only protections. You can't just write to instructions in the text section. But if you remember the dynamic linking lecture, that's not how a function call gets made. It's not a direct call to some dynamically loaded library. It goes to the global offset table, which is just a table full of function pointers. And the idea is this check certificate function is going to make a call to RSA public decrypt. It'll jump into the global offset table and jump to whatever the global offset table points to. And because the global offset table has to be kind of populated dynamically, at least during some points in program execution, it has to be populated. And so it has to be written to. So our new idea can be, it kind of makes for a very natural way to hijack a function. If you overwrite the global offset table, now you get to hijack that function, and it thinks it's calling RSA public decrypt, and it's actually calling evil RSA public decrypt. And so that's kind of our first big picture overview of how this works. We want to hijack this function call via the global offset table, via modifying the global offset table. There are kind of a lot more challenges that go along with this. One of them is that first question I mentioned, which is how do we actually get our code as a shared library to execute? And a second one is this security feature, which is relocation read-only. It's called RelRo. It's this security feature that recognizes the ease of hijacking functions via the global offset table. And so it's basically a security feature that negates it kind of disables what Jay described in his dynamic linking lecture of this kind of lazy dynamic linking, where the global offset table starts empty and then gets lazily populated as functions are called. This security feature, it's just like a certain flag that you can set, forces the dynamic linker to actually do all of the resolutions immediately right at the beginning, and fix up the global offset table before it actually calls any SSHD code, and then mark it as read-only. And so that throws a wrench to our problem, because even if we get called regularly, even if SSHD calls our library, we can't modify the global offset table because it's marked as read-only, and just like the text section will run it, our program will crash. We can solve both of these with some kind of obscure dynamic linker feature, which is this GNU indirect functions feature. And it doesn't matter too much how the feature actually works, but really what it is it allows kind of any shared library to get arbitrary code executed at load time. Right at the beginning, when it's doing all of this loading up initially because of this RelRo security feature, it allows our shared library to get some code execution. And so, like I said, it doesn't matter all that much, but what it's made for is it allows developers to define multiple implementations for a certain function. So maybe you have an implementation of a function that works better for a particular hardware accelerator, and so you want to be able to, at runtime, check, does that acceleration exist, and if so, use this faster version of the function. And the way that it works is the shared library itself, not the main code. The shared library itself gets to define a function called a resolver, and that resolver, it marks it with that attribute. You can see it's done there. The resolver function then gets, the dynamic linker kind of recognizes that. The compiler and the linker work together to recognize that and say, when they're actually trying to resolve the symbol that the resolver is defined for, they'll say, okay, I'm not just going to populate it by whichever symbol matches the name that I have. Instead, I'm going to call this resolver, which is just arbitrary code, and I'll populate the global offset table with whatever the resolver returns. So the actual details of the symbol stuff doesn't really matter. It doesn't matter what symbol this is for. As long as we define a resolver for just one of our symbols, that will get called during global offset table resolution, during that very early process. Yeah. What's up?
So this screenshot looks like
Well, what we're saying is, so liblzma crc64 is just a regular function call, for example, within our library. It's just a regular function call. But then we add that attribute there, and we say it has an ifunc resolver that is crc64 resolve. And that resolver function will choose, and this is perfectly legitimate. This is not malicious at all. It'll just choose, do I want to use the generic version, or do I want to use the version that takes advantage of this special acceleration? So this is all perfectly legitimate. But what it does give us as a library, it gives us the ability to execute arbitrary code at kind of load time. It allows us to execute code super early before any regular SSHD code gets run. And so now we can solve both of those problems at once. We can solve the execution. We can just define one of these resolver functions that gives us code execution. And then we can also, because it's called so early, we get to mess with the global offset table before it gets set write only. So you can see in CRC ifunc resolve, global offset tables, you can see there are permissions I have on the right. They're both still writable because the global offset table is actively being populated. And then later on, and so we can do our kind of modification then before, like in the resolver, in this simple version, we can do it in the resolver. We can do this global offset table update, and you will later on, when SSHD start is actually called, when the program normally starts to run, we'll be kind of locked in with our evil version of this function. Yeah, what's up?
Does the evil follow a legitimate function? Because from before, like showed that if there is no magic number, you actually need to use the regular encryption.
Yeah. I don't, it basically does. It doesn't, I don't think it actually makes the call. I'm not 100% sure. But I think it does the exact same thing. Because it wants to, like, if the certificate is not valid, it obviously wants it to go unnoticed. So it wants to just reject it or accept it as if it was a normal certificate. So yeah, I don't know if it actually makes that specific function call. But yeah, so what we can do is we can just, in the resolver, we do this global offset table fixing up. And then, like I said, we can still write to things before the global offset table is mapped read-only. And then we can lock in here, and then we've got our exploit is actually in place. That's still not quite good enough. There's still a problem with that. And the problem is this CRC resolve function gets called early. It actually gets called too early. So it gets called before, because the liblsuma symbols get resolved before the SSHD symbols, just because of how this kind of works, just because of how the linker is implemented, our symbols get resolved, and so our resolver gets called long before SSHD symbols get resolved. So the problem is, if we do all of our malicious setup in our resolver, then later on the linker is just going to come by and overwrite it and redo things, because that's kind of how it's implemented. It'll go through and just overwrite all the work that we did, and then it'll be pointless anyway because we've gotten kind of it'll just overwrite our evil pointer with the correct pointer later on, and then what gets locked in is again the kind of original non-evil version of the function. And so we kind of have there's kind of this Goldilocks zone. If we can't update the global offset table too late, because then it's marked as read-only, and we can't update it too early because then it'll just get overwritten by the linker later on. So we have to update right in this little tiny Goldilocks zone after SSHD or after the linker has resolved this symbol, but before it's actually started running SSHD's entry point code. And so to kind of get into this Goldilocks zone, we actually use another obscure linker feature, which is runtime dynamic linker audit hooks. And this is another feature. It's, again, the details don't matter too much. It's if, let's say you wanted to trace the linking process very in detail. What it basically allows you to do is define, through some other method, it allows you to define a callback that will get called at exactly when a function gets resolved, or exactly when a symbol gets resolved. And it'll just basically call a particular function pointer stored in, so ldlinux.so, that's the dynamic linker itself. It gets loaded into memory just like any other shared library. And inside it has a data section, and in that data section it has this structure. And this structure has a function pointer in it that will get called whenever a particular symbol gets resolved. And as a result, that gives us a way to kind of ensure that we get called in that Goldilocks zone. If we can somehow overwrite that pointer in ldlinux.so, what we can do is we can kind of split our malicious setup into two parts. The first part still happens in that resolver super early, but all that does is set up the audit hook later, and it sets up the audit hook later by messing with ldlinux.so. It overwrites that function pointer in its data section, which points to backdoor setup, which is kind of our stage 2 setup. And that stage 2 setup is what actually does the global offset table overwrite. That one will actually overwrite the global offset table like before, because we know that only gets called in that kind of Goldilocks zone. And that's kind of, yeah.
So I'm following all this. I have a question. This all requires you to find the exact place where to overwrite something. First, Lisma needs to overwrite the DL audit struct, right? How does it know where it even is in the executable? And then that callback needs to modify the GOT of the SSHD. How does it know where that is?
You predicted my next slide. That's actually, yeah, that's the exact problem here, is that I've assumed we can just jump around in memory, and usually we do that with the dynamic linker, but it's too early. Nothing's been resolved yet, so we can't actually do that. And this is where the implementation of the malware gets kind of crazy, because it does have to do exactly what you're talking about. It has to jump around in memory and find all these things by hand without relying on the dynamic linker. And so it does this in a lot of different ways, and it gets pretty complex pretty quickly. But the very first task in doing this is in the resolver function, it wants to get to that DL audit symbind function pointer. And in order to do that, it has to find ldlinux.so at all. So that's kind of its first task is it needs to figure out where, because those are dynamically loaded. They could be loaded kind of anywhere relative to each other. So it has to find where in memory is ldlinux.so stored. And kind of the key piece of information we use to do that is this CRC64 resolve return address. So if you look in the stack, this resolver, it's called by the linker. That's how we actually get to run during link time. And so that return address actually points back to the linker itself. Somewhere in the text section of the linker, there's this some LD caller function that then will call the CRC resolver. So during our resolver, we can look at the return address, and now we know where LD Linux is. And that's actually not the only way. They do another interesting way, which involves actually disassembling the procedural linkage table. But this is the simpler way that they do just to find this DL audit symbind hook. So that gets us part of the way there, but it's still not all the way. We still have one location in the text section of LD Linux, but we don't actually know where we are in the text section of LD Linux. And so the way that we kind of orient ourselves is by finding the elf header. So all these things loaded in memory have an elf header loaded into memory. And so what we can do, and what the malware does, is it just starts scanning backwards. It just like looks at that address and just starts scanning backwards until it finds this ELF magic. And if it finds the ELF magic, that means, oh, I know where ldlinux.so is. I can cast that, just like you guys did in one of your assignments. You can cast that to a particular structure and find a bunch of information about ldlinux.so. Yeah, go ahead.
Is that robust? I mean, like, how long is this? I mean, not that, like, I'm trying to do this myself, but, like, you know, like, it's possible that some combination of instructions happens to form the L.
Yeah, it's not robust at all. But one of the things that this malware does really well, and it really focuses on, is it does everything. It does tons and tons of verification that it's actually done things correctly. And in any case where something even seems to be a little bit wrong, it just makes all of its calls not. It just like cleans up and exits so that it doesn't get noticed. And it's trying really hard to kind of only, and this is why I mentioned it actually does this two ways. So this, maybe the return address on the stack somehow is not accurate. It actually does this two ways, checks are they near each other, and if they're near each other, only then does it proceed. So it makes a lot of effort to specifically ensure that things are actually going right. But yeah, so we can find the elf header. We have the elf header. Once again, that's not quite enough information, and this is where it gets like really crazy. Because now, assuming we have the elf header, we can find different sections, but we can't actually find the location of specific variables yet. So what they do is they implement a partial x86 disassembler inside the malware that jumps into the text section, scans for a specific load instruction that they know, a LEA instruction, which loads from memory, that they know will contain the offset to the data section, to a particular element in the data section, that then that structure is the DL audit structure, which contains this function callback that we're looking for. So it actually goes through, it uses a string, which it knows where the strings are, and strings are very easy to find in memory. It finds the memory address of a string, then looks at memory address, scans through, because it looks for like an assert statement, which includes just a string literal. It finds a string literal, looks for where that string literal is called in the text section, and it knows where that's called in the text section, knows that's relatively close to this LEA instruction, which includes the pointer or the offset to the DL audit structure, and then it disassembles that LEA, or it kind of scans and starts disassembling until it finds that LEA instruction, and once it does, it uses that offset to actually calculate this DL audit resolver function. And that's kind of it. It does a bunch of more other stuff. Like you mentioned that it needs to find the global offset table, and it still does. But once it can like walk around in ldlinux.so, it's kind of there because ldlinux.so knows about everything. It knows where everything is in memory. And if you can kind of do this process of running around disassembling things and calculating offsets, you can kind of continue on this process to find out whatever you need to know. Like I have this pointer on here, the DL Linux, it has some location in memory where it points to where the SSH elf header is, and so you can use that to find the global offset table. And you can kind of, once you're in ldlinux.so and parsing it up, you can kind of orient yourself and figure out where everything else is in the code and basically do all this. What would have been done by the dynamic linker, you can do it by hand. And so that was a lot, but that kind of gets us to the final state. And there's more complexity, but that's the basic idea of how all this works. So I'm going to run through one more time just the full sequence of events that happens in when this backdoor is called. So it starts, SSHD starts, and it loads this ldlinux.so. That's the linker. It gets loaded into memory. The linker is loaded into memory. It starts doing its thing. It starts resolving symbols. Eventually, it starts resolving the lib lzmeta.so, our malicious shared object file. It starts resolving our symbols. That involves calling this CRC64 resolve, our resolver, which is our kind of very first entry point. That very first entry point retrieves its own return address from the stack, which is the thing that we know points somewhere in the text section of ldlinux.so. Then we scan the bytes behind that return address until we find the elf header. Once we found the elf header, we use the elf header to get to the text section and do some disassembly and figure out the offset of the DL audit and all the other information that we need from ldlinux.so. Once we have that, things get easier. We can just overwrite that with our backdoor setup and then return control back to the linker, and the linker goes on and continues to resolve all the rest of its symbols. And then eventually, it's going to resolve RSA public decrypt. It'll call our particular callback function that we set up. Our callback function will do the actual global offset table overwrite and fix up this fix the global offset table to point to our malicious version of this RSA public decrypt function. And then it'll, again, just return control back to the linker, which will finish up, start executing SSHD. And then SSHD will sit around waiting for a connection. And if a connection is received, it'll decrypt the SSH certificate, think it's calling RSA public decrypt, actually call our malicious version, which will do this kind of formatting check and execution with system. So I do have one last slide that's just kind of the structure of this command, but it doesn't matter a whole lot. It's kind of encrypted twice and packaged into an SSH certificate. But at the end, there's just a particular command stored in the last 121 bytes of this SSH certificate that it executes using this kind of system call. So I know that was kind of a lot, all one after the other. Are there questions on this overall structure of how the malware actually works? Yeah.
Just want to clarify, all this very complicated setup stuff, 1 through 5, only happens once, which is when SSH.
Yes, that should only happen at the very beginning when SSH is loaded.
So like one of the reasons this was noticed, Microsoft engineered noticed 500 milliseconds of latency.
Yeah.
Where was that latency being spent? Was it due to the startup, or was it on every connection?
That's a good question. So the performance was actually, that was noticed on every connection. It was every time a connection was messed with. I don't actually know. I had the same question. Is that, so there are two plausible theories, and I don't know which one of these is right. One is that it's just doing more on an individual connection. I've kind of glossed over the evil RSA public decrypt. It's possible that all that encryption stuff and it's possible that it's somehow inefficient and it actually is causing the delay somehow. The other thing I was thinking of is potentially, depending on how SSHD is implemented, SSHD might fork if it gets a new connection, and forking could invoke some of this dynamic linker stuff. But I'm not convinced one way or the other. I don't actually know the answer to the question of what specifically is causing the latency. But yeah, that was one of the ways that it was noticed, was because SSHD was on connections, it was slowing down.
I've been trying to wrap my head around, are there any inherent design flaws in audit hooks or iFunk?
Yeah.
It's is that it? It's just
and that's yeah.
It's just flawed as is. This is the kind of thing you can do as a result. Is there anything that we could have added to these two utilities to prevent something like this? I can't think of it.
Yeah, I think there's going to be a lot of conversation about that. I think fundamentally there really isn't, because this is not the only way they could have done this. I think the ultimate problem is once a shared object gets loaded into your memory address space as a shared object, it's kind of game over. They kind of can do, there's just trying to restrict a shared object from being able to do anything would kind of restrict all the actual shared objects that you actually want to use. So it's kind of, I think, once you've gotten into the memory address space, I think it's a little bit too far, and there's not really a good way to harden. I mean, there could be some specific changes we can make, but I don't think there's really a way. I think you have to kind of prevent the shared object from originally getting loaded into memory. And I think that's what I think Brendan was identified earlier, was why does it actually link in so many things dynamically? That's probably our best bet for reducing the attack surface, is just let's not dynamically link in so many random libraries. Yeah.
Yeah, just a related question to that. I guess just what is the intended use case auditing callback setup? Because it sounds like a profiling debugging thing that I wouldn't be running on production stuff anyway.
Yeah, and because it's usually null, so usually it doesn't actually really affect performance other than one extra global variable sitting there, one extra pointer sitting there. So usually it's completely it's a no up, nothing really happens. I believe the main thing that I saw for it was profiling and tracing things. I could see maybe a really complicated shared library wants to do some other complicated stuff and it's actually it's a little more complicated than just a single callback that happens when every function is resolved. You can define more things. You can define something like on, when my shared object file is loaded, run this stuff that does these certain things. So I could see a more complicated shared object might have a legitimate use for it, but I don't know the specific detail.
Public and private code, or rather like the stuff that's tracked by Git and then the stuff that's part of the payload, right? Like what was auditable through the Git history? Because the iPhone stuff, like that was actually all like in the open.
Yes.
Like, at what point does it jump into the injected binary in the test case?
Yeah. So that was pretty much exactly what it was in the iFunc stuff. So the resolver function calls this function get it's actually like the legitimate function is underscore get CPU, and they define a function underscore get CPU, or maybe it's backwards. But then in flight, that's what they modified. In flight, when it was compiling, they modified the CRC, the resolver function, which was, like you said, publicly in the Git repository. They modify that function to in flight call all their setup, and at that point, it's all stuff that was stored in that test binary, and so it's stuff that's not tracked by Git, or at least not openly tracked by Git. Are there any other questions? Yeah.
Can you also briefly go over which of these sections
Yeah.
are able to be by libc?
Yeah, totally. So in general, the text sections are always going to be read-only because you really don't want to be modifying code in general. And this is something that Linux does as a security feature. And then, I've drawn this as a single data section. It does get more complicated than that because all these rewrite permissions can change over the course of the program running. So there's kind of two clear times. There's the linker is actually running before it's called SSHD's entry point. And at that point, a lot of this data stuff is read and writable. It can be both read and written to. But a lot of it, and that includes the global offset tables. When the linker is actually finishing up and starting to run SSH code itself, it's going to mark a lot of that stuff as read-only. So the data section, parts of the data section are actually a different section that gets marked as read-only. Some parts of the data section, stuff that actually has to be run during actual execution of the code, that's going to be, stay writable. That's pretty much the main thing that is writable is the data section, and I mean obviously also the stack and the heap and all that stuff. But all these the text sections, the global offset tables, constant data, things like this callback function, those are all going to be marked read-only as soon as the linker is about to transfer control to SSHD.
And is there
Mhm.
and when it
Mhm.
how does the new library, the malicious library, have the permission to
Yeah, so and that's the point of this DL audit hook is that that's actually an intended use case. Something that you potentially could do in a DL audit hook is define a function that then goes in and messes with and changes what a symbol resolves to. And so that's actually intended, and so it'll kind of the implementation of LD Linux is made such that the DL audit hook gets to run while the global offset table is still exactly. Okay. Yeah, so like I said, this is just the format, and there's actually, just recently, in the past couple days, more people and in the past couple weeks, people have kind of started to realize that there might be more functionality. There might be a lot of different versions of these commands. The one that I've gone through gets us root code execution though, so other stuff doesn't matter that much once you can execute commands as a root process. But yeah, the kind of next section is basically, and I'll try and go through this a little bit quickly, but all of this stuff, I've just kind of presented how the malware actually works, but all of that stuff had to be understood somehow. And malware authors, usually when they distribute malware, particularly if it's a compiled C binary, they don't give us source code. And so reverse engineering is kind of this process of taking a compiled binary, in this case, what was actually stored in the binary test file, and looking through the assembly, and actually generating some kind of C pseudocode from it. And that's kind of not an easy process because the C compiler is really lossy. You lose a lot of information when you compile a C program into x86 assembly, particularly if the author of that, in this case the malware, doesn't want you to be able to reverse engineer it easily. They can mess with debug symbols, they can do funky calls, they can do anti-disassembly stuff, they can do a bunch of techniques for how they write and compile the source code to make it really hard to get back to some kind of C pseudocode that we can understand, or even just kind of a general understanding of how the malware works. And we use tools. There are a number of different tools that help with this, things like IDA or Ghidra. These are all like kind of advanced versions of object dump and GDB. They let you kind of view x86 assembly, and that's how, I mean, any kind of assembly, but in this case, x86 assembly, and you kind of use those tools to work backwards manually from just that object file, which is just x86 assembly, and work backwards to actually come up with some kind of like pseudocode for how this actually would have looked in C. So I won't go in too much detail into like what IDA looks like. This is just some screenshots from IDA. You can see this is actually like a very simple like entry point where it just is making a couple of function calls, but already it like fills up a slide. It's relatively hard to read, but that's what the process of reverse engineering looks like, and it involves like going through this code and labeling things. So initially, all these calls, they have either no name, or they're named something intentionally obfuscating, and so you have to kind of go through and figure out what all these variables are, figure out how functions are set up, and kind of disassemble this manually until you can convert it into C code. So in this case, what you can see, this is that get CPU ID function, that malicious thing that's called by the resolver. And it calls this function that I've called backdoor entry, which calls another function, which calls backdoor init, which then does, this is one of those examples of what I was talking about of the malware authors like intentionally making things hard to disassemble and to reverse engineer. This whole code block, it's actually just a function call, and it is not calling what you think it's calling. It's doing this really kind of slippery thing where it modifies the global offset table, makes the function call, then modifies it back. And as far as I can tell, I mean, there might be other reasons for doing this. As far as I can tell, that's just to make it annoying to reverse engineer this and just to prevent like automated disassemblers from actually working. But yeah, it's really slow. You have to do this kind of manually. And luckily, there were a bunch of people out there who are actually doing this in the public. And that's where a lot of like my understanding of this code comes from public reverse engineering projects. Like, I mean, I didn't go through and reverse engineer all this. But usually, eventually, you can kind of turn it into something like C pseudocode. So for the rest of these key points where I'm actually going to show what the malware code kind of looks like, it's all C pseudocode, and it's very pseudocode-y. Like, I've cleaned it up as much as I can to just kind of get the general idea. And I won't go through these in too much detail, but these are just some of the key points. So this key point is that moment where it's actually scanning to find the LD Linux elf header. So you can see on this side over here, this is what I was saying. It calculates it in two ways, once with the resolver and once by actually disassembling the procedural linkage table. It checks the difference. If they're too far apart, it means something went wrong and just exits quietly. Then it masks to get a page line value and just searches in 4096 bytes because elf headers are page lined, and searches using this like kind of well-hidden string checking function to check if it matches the string elf magic. And if it does, it's found it, and it just casts it as a header and just goes on to continue the rest of the malware. Then this is another key point. Once again, it's not super important to like understand everything in a ton of detail, but this is just to show you a picture of what it kind of looks like. This is where it kind of calls all this disassembly stuff. This is, given the elf header, how can we go in and actually find this particular structure that we're looking for? And in this case, you can see in the very upper right, this is the code. This is the code that we're actually searching for, disassembling to try and find, because it gets this structure on this DL unaudit thing. That's a global variable. And this assert statement, because of how assert statements work, they include string literals of the code themselves, so they're very identifiable. So you can go through, and what the malware actually does is it goes and finds the string literal. Then, and you can see, yeah, it finds the string literal here. Then next, it actually goes through and searches for instructions that reference that string literal. And then once it finds that, once it has that instruction, it searches in the 128 bytes nearby, because that means it's in this assert statement, in the instruction that references the string literal in the assert statement, but now it needs to search around and find the actual load effective address, LEA instruction, that has the offset we're looking for. And so it just, you can see it just looks through, tries to call this disassemble function, which actually does disassembly of the instruction, checks some features of it if it looks right, and then makes sure it points to somewhere in the right section. And if it doesn't, everything exits very quietly. But if it does, then it now has a pointer to this DL and audit structure. And it's right next to the DL audit structure in memory, so it can kind of get everything it needs from there. And then things get a little bit simpler. Once again, this is super pseudocode-y, but they make a fake symbol like DL audit structure, which includes their fake function call, their fake callback function, overwrite the real audit structure that exists in ldlinux.so, and then continue on with the malware, continue on with ldlinux.so, which eventually calls, this is that DL audit symbind function, and it has kind of a standard prototype, and it does a pretty simple thing of, it's actually called on every symbol resolution in SSHD, and so it just checks, is it this RSA public decrypt? If it is, overwrites the global offset table entry here, using some information that it's stored previously. So that's kind of all that was just a little bit of taste of what reverse engineering kind of looks like. It starts in IDA, and then you move to see pseudocode, and once you get pseudocode, then that's something that you can kind of share with people more generally. And that's what all these reverse engineering projects are actively doing, is they're trying to convert that assembly code into the relevant C or C pseudocode. And the last year, I won't talk about this too much, but a lot of the things in here, a lot of the things that I did end up removing from the C pseudocode is avoiding detection. This was something that they tried really hard to do, because you can imagine this is a piece of malware that's going to be running on potentially millions of Linux servers in a relatively, in a process that is super ubiquitous. People are probably going to be doing lots of profiling and lots of examinations of it just normally, and you don't want to be detected. You want to change the behavior in any way, and you want to kind of make analysis as hard as possible. So some of the ways they did that, they have lots of anti-debugging stuff. So people, if it detects a debugger, it checks for breakpoints. If you remember how breakpoints are implemented, they overwrite certain bytes. That's really easy to detect. The malware actually checks, are there breakpoints within itself? And if there are, it kind of changes itself to be like innocuous. It kind of, it converts its calls into basically NOPs and makes itself look, not at all malicious. And it also includes a bunch of environmental checks. So it only executes if it's, this is what I was saying before, it only executes if it's sure that it can actually work. It checks for a bunch of, parameters of LD Linux and environment variables and things that make sure that it's only going to actually run if it's sure that it can run successfully. One of these is actually a kill switch. So this is something that's sometimes malware authors insert if they want to maybe they don't want to infect their own systems. It's a particular environment variable that gets set. If that's set, the malware just exits and will never run, if that environment variable is present. They also do a lot of general obfuscation, like those indirect function calls. They obviously don't make lots of system calls because system calls are relatively easy to track. And they also, I didn't talk about the meaning. They have this prefix tree, which is kind of a way that they avoid just having the strings they look for visible in the function. It's kind of this obfuscation method of hiding strings. So all of this kind of points to something that's really carefully designed, and they're very concerned about letting this backdoor, sit for as long as possible and kind of getting as much access for the can as long as possible and avoiding detection as much as they can. And so now I think we'll see if this works. Oh yeah, go ahead.
I saw that in the setup pseudocode.
Yeah.
There is this hook that calls the audit hook. So
Yeah.
if somebody were legitimately trying to use the audit hook, say to trace stuff like that, would that get clobbered by this?
Actually, earlier on, somewhere in it checks where it sets the audit hook. I don't know if I have it in here, but what it actually does is if there's an audit hook already in place, it just doesn't run. It just exits as if it doesn't exist. So if there's an audit hook already in place, it won't, because like I said, its goal is to really only run if it's certain that it won't be detected. So now we'll see. I think we'll see if this works. So the way that this is set up, it just runs on any Debian distribution. So in theory, patching it a little bit so that we can get there, so that we can use our private keys, I should be able to actually demonstrate this working. So this right now is QEMU. It's a hypervisor, or KVM is a hypervisor that runs the QEMU runs. And so what that lets me do is kind of simulate a Debian system that is vulnerable on my system right here. And so this is just a regular Debian system. And I can, it's running, and I have it connected up to the network, so I should be able to, on my local network, I should be able to connect to root. I think it's on this port. And so now I'm connected to this Debian server. It's as if it's a server running somewhere else, and I'm connected to it, but now I'm SSH'd in. And you can see that if I'm root right now, if I look, SSHD does exist. SSHD is this long-running process. It's a binary that just sits here, user sbin SSHD. And if I do LD, which actually you're not supposed to do unless you're, it's okay because I'm in a sandbox right now. It's in a virtual machine, but on your actual computer, you're not supposed to do LDD on vulnerable or on malware. But this is fine.
Can you explain why? I thought this just lists.
It's dumb. Sometimes it actually executes things, which is kind of wild. Yeah, I didn't know this either until I was reading about this and somebody was saying don't run this on your actual computer because it actually does execute instructions, which is stupid. Yeah. But you can see, so in this list, it actually includes liblzma. And it's the particular version, it doesn't show it here, but it's a particular version that is vulnerable. And so on my computer, so this is on my computer, I have this, I didn't write this, but there is this Go script, which is a relatively simple script that just takes in a command and packages it and makes an SSH connection with that certificate, with that command packaged into the certificate. So you can see somewhere around here, I mean, Go is kind of hard to read for me at least, but it makes this SSH connection with the particular certificate. And so we'll see if it works. But this is what it looks like. I just run the main command. I give it the address of the server and the command. It's already been pre-programmed with the correct keys. And I'm giving it a command, just shut down now. And I run that, and my VM shuts down. Which that might not look that impressive, but there was no authentication there. There was no checking of passwords. There was nothing. If that was a running server on the internet, I could have done that to, anybody. Like if that was on Spock, I could have just shut down Spock without the permissions to. I was concerned. I don't know if Google Cloud would get mad at us for it, but I don't know. But yeah, so that's what it looks like, and that's really dangerous. That's kind of a big problem. If you have any installation, you could have a server that downloads the kind of official Debian image. If this had propagated far enough, somebody could download the official Debian image, install it, do all the right security configurations and stuff, but then this attacker can just send arbitrary root commands to their system, which is that's really dangerous, and it's really powerful, and could have been one of the most widespread attacks that at least has been caught. And it wasn't because it was caught so early, but it really could have been. So the next couple of sections, these should be relatively short. Oh yeah, go ahead.
Is there an effort to identify the GM?
Oh, who it is? Yeah, I mean, that's kind of what this attribution section is about, is like, how do we figure out who this person is? I mean, it's almost certainly not a single person. So in general, attribution kind of looks like, it's really hard to do, basically. And particularly for security researchers, it's hard to do. But the ultimate goal is kind of, like you were saying, exactly who is Giatan? Who is behind this attack? There are a number of different possibilities. Sometimes they're the two main categories really are nation states doing espionage, and also criminal organizations looking for kind of financial gain. People doing ransomware attacks and things like that. They're just trying to make money. Sometimes as individuals, that's I think a lot less common. Particularly for attacks of this scale. But the way that attribution usually works is you identify certain features of attacks, different like their overall technical style, the level of sophistication, how much effort went into it, and also just their motivation, what targets they selected, whether they were obviously just going after anybody who had money, or whether they're looking for sensitive government targets, something like that. You can kind of get an idea of what they're looking for, and once again the techniques they actually use and the level of the actual style of those techniques. And then usually there are a lot of organizations that kind of group different attacks, high-profile attacks, leave traces, and so based on these features, you can kind of group them together. Sometimes you give the groups names. Some of the security analysis companies give them exciting names. Other ones like Mandiant gives them kind of boring names that are just numbers. But eventually, ultimately, once these groups have been around for long enough and done multiple attacks, you can kind of trace them over a couple of attacks. Sometimes you'll get a government or some other organization will actually say who they think it is. We think this is the Russian government or something like that. That takes a long time and requires a lot of different attacks. That hasn't happened for this attack yet. And so we really don't know. In particular, we don't know who Giatan is. Probably, from the style, most people are, and this is not my analysis, this is from people who know security stuff a lot better than I do. They're kind of saying it's probably a large organization just because the level of sophistication and the amount of effort and the duration, the amount of time they're willing to spend on this one single attack and multiple people's efforts over multiple years to put this backdoor in place means that it was likely a large organization. And the level of how good they were at actually keeping their fake accounts out of how good they were at isolating their fake accounts means that this was probably at least an organization with a high level of sophistication, an organization that is relatively experienced at doing this sort of thing. And actually, I was talking to some people on Discord who were doing public reverse engineering of this, and a lot of them said the code itself felt like an organizational effort. It felt like code that was a bunch of different components being stitched together, as opposed to code that was kind of written by hand by a single person for this. So that indicates that it was probably some sort of larger organization. It seems more likely that it's a nation state as opposed to some kind of a criminal organization. It just seems like a lot of effort to go through. If you had that much effort and that much technical expertise, there's easier ways to make a lot of money more quickly. than doing this. This seems much more likely to be some kind of government organization or government sponsored or something trying to do some kind of espionage, trying to like collect intelligence on somebody. But yeah, who it is, I don't really know. I don't think anybody really knows. Could be Russia, Iran, China, North Korea. Some people said it's probably not the United States. I don't know how accurate that is. It doesn't seem like something that they would do, but I don't have enough experience to know. It does seem kind of similar to the SolarWinds backdoor. That's something that we saw, I think, a couple of years ago. This is a closed source backdoor, so they actually inserted a backdoor into SolarWinds, which is a software product. And that has been somewhat linked with a Russian group that is, I think by mandate is called APT29. So it could, some people are saying like it seems kind of similar to this whole technique of doing a backdoor, but we really have no idea who it specifically is, other than it's probably a big organization, and it seems like there's a good chance that it was a government. And it does have some large implications for open source and cybersecurity in general. And this is something that some of you guys were kind of pointing out. Yeah, go ahead.
Yeah, I'm a little bit confused. This is on GitHub, right? Can't GitHub like track this or something?
Yeah, and I mean, this is I think somebody was doing some analysis on this. It was all very well obscured. So they had the fake accounts, the accounts since the attack was discovered, the accounts are just they're just dead. Nobody's using them anymore. And they all link to kind of fake email addresses and fake IP addresses. And so there's no, and that's another indication that it was probably a relatively sophisticated group, because they didn't really make any clear mistakes, at least we haven't found them yet, of accidentally using this same email address for some other attack or something like that, or leaving behind a trace that originally leads them back. There's some interesting analysis about like time zones that suggest it might be Eastern European, but it's all inconclusive. Yeah. So yeah, this is the last little bit is just kind of what the larger implications are. Like I said, usually, and like you guys were identifying, usually there's a larger specific mistake to point to, like, oh, we accidentally reset somebody's password when we shouldn't have, or we forgot to update our encryption keys. With this attack, you could have been attacked having done everything right, having done everything by the book, no security, no issues with your security policy, and you would still get attacked, and you could still be, your information could still be stolen. There are some specific technical solutions, but I mean, they're kind of tailored to this specific attack. One of them is one that we talked about before. We could just reduce our kind of attack surface. We can reduce dynamic linking as much as we can. We can also ensure that these release tarballs match the repository source. This whole auto-config auto-tools thing is kind of a holdover, I think, from older eras of software development. It doesn't need to be that way anymore. And so having more verification that like the tarball you're downloading is actually representative of the Git repository and not just trusting the maintainer. That's another specific thing. But there's a larger problem, which is these what's called open source supply chain attacks, which is where malicious code is inserted into an open source project. There's not really a clear solution for that. So I think the implications, this is my like updated version of the webcomic, but the kind of what probably the implications will be for open source security is probably just more recognition of these types of attacks as existing. XZ Utils probably wasn't the first. I mean, there have been other examples of open source backdoors, none nearly this like extensive. But there's a reasonable chance there might be other attacks like this. I mean, it seems like it's not that hard. I mean, it took a lot of effort over a long period of time, but like for a big organization, for a big government agency, that doesn't seem that unreasonable. And so there might be other ones out there, and we don't necessarily know. Yeah, go ahead.
What does last C column do? What is their like? Yeah.
Like, what is you mean? What is he doing from now and going?
Yeah,
forward?
like what do they do outside of being burnt out of?
I actually know. I think he's Dutch. I want to say he's a software developer somewhere, I believe. I don't actually know much about him. I know this whole thing has been kind of a disaster for him. Like he already didn't. I mean, he already didn't really care about this project, and then all of a sudden, everybody in the world, every security researcher in the world is looking at his project, examining, and he's going through this whole process now of like, should I rebase the repository to eliminate all these malicious commits, or should I, like, how do I? Because G10 has been contributing for years, so how do you, do you roll back to the version from like, 2020, which is, at this point 4 years ago, or like, where do you go from here? And he's not getting paid for any of this, so he's just like some guy. And so that's kind of the big problem here, is that, and I have that as a lower bullet point, it's kind of problematic for critical infrastructure to depend on often anonymous hobbyists. Like, that's a pretty big problem. There are some suggestions maybe we could track maintainer identities. Like, if we knew who G10 was, if G10 had to be like associated with an identity, that could have helped. But a lot of maintainers might be uncomfortable with that, and it's not clear that it would have actually fully stopped anything. Another option would be, like, maybe we should be paying for more open source software. Maybe we should be paying maintainers. that's also problematic. Like not, like first of all, who's going to pay? Are companies probably aren't going to pay just on their own, and then maintainers might not necessarily want to pay. A lot of them already have jobs and do things as a hobbyist project. They don't want to be responsible, basically.
Why did the guy trust making this
Well, he does actually, and that was another part of this I didn't mention was this Giatan. This was the first time he showed up in XZ Utils. He had a bunch of contributions to a bunch of other open source projects. So he had a whole backstory of like, oh, I've contributed to like a bunch of these other open source repositories and seemingly legit. And now, I mean, everybody who has one of those repositories is now like looking really closely at those commits because now there's this guy who we found out was actually potentially some hacking group.
I was a bit confused. Why would paying maintainers
Well, it wouldn't necessarily be a solution, but if you have maintainers as kind of developers that are employed by somebody, then they're not just hobbyists, right? And then they have more of a sense of responsibility, and they kind of have to take security more seriously. And as a result of that, you could get more maintainers, and you could ensure that the maintainer is somebody who, like, if you're willing to pay somebody for something, there's probably a lot more people willing to do that. The number of people willing to maintain something for free, just for fun, is pretty small. And so if you pay people, you're more likely to get people who have some kind of commitment and are willing to like devote actual time to making sure that things are secure. And you can kind of, money gets you like security people who can analyze these sorts of things.
Besides, like if the SSH like overhead wasn't noticed, is there any other place that might
Yeah.
so obscure that like
Yeah, there are a couple things. So I did skip over some of the other mistakes that they made. They did make some mistakes, and they had to they did this really interesting because they had to update the binary test file because they actually made a mistake that was causing Valgrind errors. Yeah, they had a memory leak, and so a bunch of maintainers. Yeah, so a bunch of maintainers of like some testing distributions were like, why are our distributions now throwing Valgrind errors? And the XZ guys realized, oh shoot, that was our backdoor. And so they had to actually update this binary test file surreptitiously, like with a couple of commits. So people probably would have delved more into those Valgrind issues and probably would have found this. Another thing is systemd. We talked about before, why is SSHD linking in libLSB? Independent of this, people noticed that, or like, maybe we shouldn't do that. Not just for security reasons, but also for kind of performance reasons. And so they thought there was actually, in the works, there was a commit that was going to kind of remove that, basically. We're going to prevent this, which would have prevented this attack from working. So there actually probably would have been a smaller window of time, maybe a couple of months, where this was in mainline distributions, but that updated to systemd wasn't. So if this hadn't been caught, and if the Valgrind errors hadn't been caught, it's reasonable to think they probably would have had a couple of months of free reign on people's machines, unless they did something that got them noticed. And another thing is, because of the way this is actually not logged. Like usually an SSH connection gets put into logs somewhere, and so somebody doing analysis could be like, why is this person SSHing into our server? Because we're in SSHD, one of the things they actually do is if it's their special magic certificate, they throw away some of the logs and they reduce the logging. They don't do it perfectly, but they do a pretty good job of making it so that it appears that it never happened. And so it's reasonable to think that they might have gotten away with it for quite some time, long enough to do a lot of damage. Yeah.
If they were they almost got there and it was discovered by like coincidence,
Mm-hmm.
aren't the odds really high that something like this is in the wild somewhere? And maybe like as system I don't know.
Yeah, I mean, that's what a lot of people are scared of, is that like it's possible that this was relatively sophisticated. This require a lot of technical sophistication, and even with all the technical sophistication, there were problems. Like they did have those Valgrind errors, and they had these performance issues. So I don't know. I mean, it's kind of, that's something that people are thinking about. It's like, how likely is it there are other ones out there? But I think people in open source in general are taking it a little bit more seriously, that this is something that actually does happen. But yeah, no, that's something that people I think are worried about. But there's arguments as to whether or not it was really discovered purely by accident, or there were so many mistakes that they made that it probably would have been discovered anyway. Yeah, Dol. Yeah, they did, because OSS Fuzz is this project that like fuzzes a bunch of open source projects, and they didn't want their stuff getting fuzzed because fuzzing is a technique in security that like kind of does some kind of input generation and checks if checks like how it kind of recognizes weird code paths in applications, and so. I think, I don't know the exact, but I think they did go in and actually like request or disable OSS fuzzing on their repository, which I don't know enough about that process to know how normal that is or how much suspicion that would have raised.
Yeah, apparently what they did was, so the iFunk thing is like a linker-specific feature, right?
Mm-hmm.
So there's a check in CMake that says, does this compile? And like, if it doesn't compile, then iFunk probably doesn't exist, and so like there's no point compiling with iFunk.
Mm-hmm.
Right. So then in their commit, their like test, they inserted a dot, which caused a syntax error, caused compilation to fail, and so iFunk doesn't exist across any of the OSS fuzz builds. Therefore, it was never fuzzed in the first place.
Okay. Yeah. So that sounds like what they did. And I think maybe people would have caught on to that. I really don't know. Are there any kind of other questions about the thing as a whole, or I mean, I do have one more slide, which is just kind of general takeaways for ASP. This is kind of what I've learned as I've gotten more into cybersecurity in the past couple semesters. And the first one is that software engineers, like, we're all, no matter whether or not you're actually going to go into security, security kind of touches all of software engineering, and anybody who's working with software has to kind of have an understanding of security. Like, this was caught because a regular developer for Postgres had enough of an awareness of security to say, this looks like a backdoor, something's going wrong here. So I think it's really important, like, for all of us, whether or not we're going to go into security, to be aware that this is things that happen. And as a part of that, something that, like, I experienced before I got into this stuff was that I was kind of afraid of cybersecurity. It felt like this kind of black box, this magic, like, oh, malicious code. And what I found, at least this part of security, is generally often just applied systems programming. It's just all the things we were learning, dynamic linking, loading, x86 assembly, all that sort of stuff. Like, that's just systems programming. It's just applied in ways to, like, find vulnerabilities. And so it's like, I think you guys have, like, a super excellent base to get into stuff if you are interested in security. I wouldn't, like, that was something I waited a long time because I was just afraid of like it being too complicated, but it really is just systems programming. And particular things if you're more interested in this in the future, next fall there's this class, malware reverse engineering and analysis. It goes really in depth into reverse engineering and specifically like taking malware and reverse engineering, but you also get a kind of overview of different types of malware and what malware looks like in the real world. And the professor tells all these stories because he actually worked in the cybersecurity industry. And then if you're just interested in security more generally, you can join CU Cyber. It's a club that I'm a part of, and we meet every week. It's relatively chill, but sometimes they have interesting speakers and lectures on different topics and some career stuff too if you're interested in cyber careers. So the website there's like Slack and mailing lists and things like that. So definitely if you're interested in security, it's a great, like, that's where most of my learning of security has been through CU Cyber and through the reverse engineering class. But yeah, that's pretty much all I got. I do have some like sources at the end if you guys want to read more. There's lots of, specifically